Depending on your time zone, good morning, good afternoon, or good evening. I'd like to welcome everyone to Solving Tomorrow's AI DL Scaling Problems today. This webinar is presented by AIC, AMD, Cirrascale, and KIOXIA. My name is Joe Kempler from AIC's Office of the CTO, and I'll be your moderator today. Before we start in the classroom, let me provide a quick overview of the webinar's format and some quick start tips. The webinar is broken down into 4 presentations: Cirrascale, AIC, KIOXIA, and AMD. If you would like to ask any questions, please type them into the question box and they will be answered during the Q&A sessions at the end of the presentations. For additional discussions with any of the presenters, there will be 4 separate Zoom rooms open at the end of the webinar that will allow you to dig deeper into any of the technologies. Lastly, all of the presentations are available for download from the handout sections of GoToWebinar and will be posted to AICIPC.com for future reference. AIC is excited to host 4 high-powered presenters today. The first will be Cirrascale's CTO, Dave Driggers, and he will outline the customer solution. The second presenter will be AIC's own Alan Yu. Alan will discuss Gen 4 ultra-high-performance storage servers. KIOXIA's Matt Hallberg will be following and update the audience on Gen 4 NVMe SSDs. AMD's Madhu Indurthri will highlight the performance advantages of AMD's EPYC 7000 series processors. Here's Cirrascale's presentation, Scaling to Solve Tomorrow's AI DL Problems Today. Dave, take it away.
Hi, I'm David Driggers, founder and CTO of Cirrascale Cloud Services. My main role in the company is being the chief architect of our platform as a service for HPC, AI, and deep learning. I have been building large-scale HPC clusters for over 20 years. Today, we'll be presenting a webinar that tackles the challenges of tomorrow's fast-evolving AI and deep learning marketplace. In particular, we are focusing on the huge problem of handling massive amounts of data and the scaling issues that dealing with this much data creates. First, a little background on us. Cirrascale has been dealing with problems of scale for well over a decade. Before becoming a cloud services company, Cirrascale was an HPC server and storage manufacturer that targeted the most difficult high-performance computing workloads. We built large-scale compute clusters for oil and gas, financial services, and EDA companies, the likes of Shell, Morgan Stanley, and Qualcomm. The systems we built had hundreds or thousands of servers, handling hundreds of terabytes, sometimes even petabytes of data. And this was when a petabyte of data was almost unheard of. There were certainly problems of scaling that needed to be tackled then, but it was mostly scaling out. Then a monster breakthrough happened. GPU-based computing became the next big thing. Our company was actually the first to design and build an 8 GPU beast of a server in 2012. Too bad it was bigger than what most software applications could take advantage of at the time, so we waited for wider adoption. Then the AI revolution began, and we were off to the races, trying to keep up with the ideas that the data scientists were coming up with, now that they could chew on massive amounts of data. We have been fortunate enough to continue to work with the first movers in AI, like Uber, Lyft, OpenAI, Samsung, and of course, NVIDIA and AMD. Living on the cutting edge, we get to see the problems before most people even know they exist. Tomorrow's challenges are more complex because we're now needing to scale in nearly every direction, up, out, even in latency. This is primarily because the data we're trying to make sense of is so rich and diverse. With the advent of deep learning and its sister machine learning, we're now able to look at data in a whole new way, in a much larger way. We are not your normal cloud provider like AWS, Azure, or Google Cloud. We are a fast mover that enable the latest products from multiple partners. You will find next-generation technology in our cloud from NVIDIA, GraphCore, AMD, and many others. We are a company that focuses on production workloads and getting the job done in a consistent, predictable manner. We don't use virtualization. We don't have variable billing. What your bill starts as is what it ends as. We do believe there is certainly a place for both on-prem and hyperscalers, so we embrace and fully support both hybrid and multi-cloud scenarios. The hyperscalers are fantastic at being elastic, whereas we focus on long-term, consistent usage scenarios. We even support having AWS Outposts and Azure Edge appliances in our footprint for companies that must have the tools they've come to rely upon from the big guys. Finally, as you can probably tell, we do not believe in a one-size-fits-all model. Instead, we work with our clients to tailor a solution to their needs that is optimized for their workflow. Cost, performance, scalability, that's what we focus on. At Cirrascale, we're not just providing a simple resource like a CPU, a GPU, or even a chunk of storage. Instead, we look at the whole application, its workflow, and then build a platform to deliver a total solution. We have a particular interest in deep learning applications due to the nature of them being some of the toughest but most exciting challenges that are being tackled today. We take a heavy hand in optimizing the platform, effectively being a consulting partner and taking over the DevOps wherever we can to add value and free the data scientists to focus on their true work rather than dealing with the IT stuff. We do this predominantly with accelerators like GPUs, IPUs, and FPGAs connected with high-speed networking being fed by the fastest flash-based storage available. The primary targets for our cloud service are AI applications that are handling large amounts of data. This occurs when the data is rich or just massive in scale. We're seeing lots of challenges and opportunities in processing medical image data from X-rays and MRIs, diverse data coming in from cameras, LiDARs, and sensors off of vehicles and robots, as well as images and video from satellites and drones. The other big challenge area is around natural language processing. In order to improve the accuracy to the level of really being able to emulate a human, the amount of data to be processed and the compute power required to process that data is truly staggering. GPT-3, the state-of-the-art NLP application for OpenAI, has 175 billion parameters, whereas the previous model, GPT-2, was only 1.5 billion. This is where we are headed. Orders of magnitudes in increases in the data and the processing to get to the next steps of accuracy. Similar jumps are required to improve recommendation engines that more and more service providers are trying to use to sell more things and provide better advice on related content that customers may like. We were fortunate enough to work with OpenAI for a number of years and learned a lot about scaling specific to their applications. OpenAI initially needed to remove bottlenecks that were primarily related to the I/O between the GPUs, first inside the server, then ultimately between the servers connecting to each other. We accomplished this by building bigger servers in the beginning. The standard was an 8 GPU server, which at the time was the largest building block available. This was great for a while, but as our application grew, the bottleneck moved to connecting the servers together. We ultimately connected them with a high-performance Mellanox-based network. Finally, for GPT-3, Microsoft built them a monster system of 285,000 CPU cores with 10,000 GPUs, all connected via a 400 gigabit network to complete the training of the model. Lucky for them, they were not dealing with a massive amount of data. Instead, they were creating their own data on the fly, and the data created in deep learning is typically pretty small. This is certainly not the case in automating vehicles. The main topic of this webinar is tackling tomorrow's problems with today's technology. One of the most active areas of AI development is on automated vehicles. Even if just simply helping us to drive safer or park better, the amount of data that needs to be computed to enable these technologies is significant. For level 5, which is complete driverless automation, the numbers are truly staggering. Most modern vehicles from companies like Lyft and Waymo are gathering data from 7 or more cameras, 3 or more LiDARs, as well as numerous other sensors. There are test cars generating over 20 terabytes an hour. For even a small fleet of these test vehicles, this adds up to petabytes per day. With those kinds of numbers, we had to look seriously, not just at the I/O between the GPUs, but had to figure out how to feed that much data through the systems themselves. NVIDIA's latest DGX, the A100, helps a lot in regard to this. The latest version pumped up the performance in most areas by more than 4 times the original DGX1. And with respect to the external I/O, it went even further. NVIDIA's latest, the DGX A100 80 gig, has 8 HDR InfiniBand connections dedicated for communication between the GPUs, and 2 more dual-port HDRs that are dedicated just for the storage. 400 gigabits just for the storage. Our goal was to enable those connections at full wire speed in order to feed the beast and pump as much data as we could into the servers in parallel across a full cluster of DGXs. In designing our storage, we pretty much started with a clean slate and focused on how to best match our DGX A100's storage connections. We knew it had to be HDR, and that meant PCIe Gen4. Since we wanted it now, that meant it had to be AMD based. We also did not want any additional switching inside the server. That also pointed to AMD and the 128 lanes of Gen4 PCIe that was supported by the latest EPYC ROMs. We of course needed a motherboard that was laid out with enough PCIe Gen4 to connect all the HDR cards and the Gen4 NVMe drives. We found AIC was building just such a motherboard. Did I mention Gen4 PCIe enough? We had to find NVMe drives that were also Gen4. And KIOXIA was up to the task with U.2 Gen4 drives in all the potential sizes that would allow us to scale the performance to match the desired storage capacity. We now had all the key components to build what we needed. We just had to pick a system and storage software to round out the platform. The whole reason for the POC was to identify and make a scalable building block that could be scaled all the way to the final solution. The storage needed to feed an NVIDIA SuperPod 140. That's a full bisectional HDR InfiniBand cluster with 140 DGX A100s. We found the builder of the motherboard, AIC, also had a fantastic server using the very same motherboard. The server looked almost purpose-built for our needs. We would get excellent density with the chassis holding 4 storage nodes in just 2U. This is very important when building larger InfiniBand HPC clusters because of how much more expensive the active cables are compared to the passive ones. If the cable needs to exceed 5 meters, the cost goes from about $300 to $2,000. And trust me, on a SuperPod with thousands of these cables, it can add up to ridiculous amounts of money, so every bit of density keeps the cable shorter and costs down whenever possible. Finally, we chose a supported clustered file system for AI and deep learning that was approved by our target customer, IBM's Spectrumscale ECE. Spectrumscale is the erasure code edition of what used to be called GPFS. The ECE version is highly scalable and continues to improve both in performance and efficiency the more nodes we add. It also lowers the cost per usable terabyte as you increase the number of nodes. And since we're looking at petascale storage, it adds up fast. IBM also has excellent support for innovators like us who are trying to push the envelope, as well as fantastic pricing for larger scale deployments. Definitely what we wanted to use. For our POC, we need to match our final requirement of a full bisection, non-blocking communication everywhere on the SuperPod. We were able to build a mini pod of 2 DGXs and 8 clustered storage nodes to enable this. The training data had to be as fast from the attached storage as it was from the local storage, and it also had to be capable of saturating the storage connectivity on the DGX A100s. Done and done. Also, it was in a tight, cost-effective, scalable solution. From the diagram, you can see effectively 3 networks: the compute network, the storage network, and the backend network to actually connect the storage cluster itself. We were able to do this fairly easily for this POC using a single 40-port Mellanox 8700 switch, which also happens to be the main switch used in the SuperPod 140. This POC was an exercise in math. Simple as that. Look at the performance of the storage connections on the DGX and make them exceed with the storage cluster's potential throughput. Make sure to have enough connectivity from the storage nodes themselves. Check. 6 HDRs from the storage cluster feeding 4 on the DGX A100s. Enough storage cluster backend throughput. Check. 6 HDRs there also. Enough NVMe to drive the HDR links. Again, yep. With an extra 50% available bandwidth to help saturate those links. We were very excited to be able to build a super high-performance, scalable storage solution from commonly available components that could match one of the most powerful AI and deep learning building blocks, the DGX A100, even when configured as a SuperPod. Thank you very much for your listening. Now, on to some of our partners to go deeper dives on the individual components that were used to enable this POC.
Thank you, Dave. Hello and welcome to today's webinar. My name is Alan Yu. I'm a product engineer at AIC. I would like to provide some additional information about the compute node in Cirrascale's AI and deep learning solution. As they have mentioned, their solution requires ultra-high performance with a bare minimum of latency. To meet these requirements, AIC started with the AMD's Gen4 EPYC 7000 series processor, include the highest performance Pcie Gen4 SSD from KIOXIA, and design a server from the ground up to meet their AI deep learning stringent requirement. Let me introduce you to AIC's ultra high performance storage server series, the HP 201-202-AG. I'd like to start with the problem statement. What are the key storage issues that need to be addressed in AI and deep learning architectures? In AI and deep learning, there are a couple of key requirements: massive storage and ultra-high speeds. AI and deep learning applications have millions and millions of files, and that takes massive amount of storage. To search those millions of files, every microsecond make a difference. To achieve both of these requirements, we need to start with architecting a completely balanced system. This means balancing both across media and network. Once we have the optimum engine, we need to start designing the drivetrain. This means starting with the PCBA layout. Each of the 128 Pcie Gen4 signal were routed from the processor, balancing out the media and the network signal. Keeping it balanced down to each core allow for fine-tuning to maximizing performance. Here is the completed design: AIC Aurega motherboard. With 3x16 PCIe slots in the rear, we created the highest add-in card capacity in this form factor. With 64 PCIe lanes and slimline connectors, we have the ability to connect large amount of NVMe drive without a need of a switch. With the low latency in mind, we have Pcie Gen4 from media to network. With the engine and drivetrain optimized, AIC then designed a high-performance chassis. For maximum density, we developed a multi-node design. For maximum performance, we went with AIC HP201-AG, our 2U4 node with 24 of the highest performing KIOXIA NVMe drive. To add flexibility to the solution, these can be either 3.5-inch or 2.5-inch drives. Wrapping it all together with exquisite option package. Each of the 4 nodes have access to 6 U.2 NVMe drives and 2 Sata SSD and 2 NVMe M.2. Each node not only have high storage density, but it has high expansion with 3 Pcie Gen4 by 16 slots. This unit is also very flexible with the tri-mode backplane. It can support NVMe, SAS, SATA drives. In summary, 4 nodes in the 2U space will save you rack space and therefore save you money. Each node also have the highest network support in the market with 3 PCIe by 16 for a total of 12 PCIe by 16 for the full system. Additional feature like toolless design will save you time during data center installation. Also, toolless drive design make it easier for maintenance in the data center where screws don't get along with the server. Besides the AI and machine learning, AIC product can be used in other verticals such as CDN, oil and gas, virtualization, and automation. Oil and gas applications such as pipe inspection and geoscanning creates terabytes of data that need to be processed and stored. Virtualization creates small packets of data for VM and containers. These containers require low latency to improve performance. For self-driving cars, it generates 1 gigabyte of data a second that need to be processed, stored, and uploaded. These are some of the verticals AIC products show themselves to be the best in class. I'd like to thank you for your time. And if you have any question about AI and deep learning and how AIC had designed the perfect storage server for this application, please join me after the last presentation in AIC Zoom room. Next, we have KIOXIA's Matt Halbert to discuss their Pcie Gen4 SSD. Matt, take it away.
Hi everyone, welcome to my part of the presentation, KIOXIA. Let me bring up my slides. All right, so my name is Matt Hallberg, and I gotta come into an introduction here pretty quick. My name is Matt Hallberg. I'm the Senior Product Manager over at KIOXIA, responsible for our enterprise NVMe and Ethernet SSDs. Been in the market for the industry for a long time, the storage industry, over 18 years. Dealing with lots of fun protocols that you probably are familiar with, like InfiniBand or Fiber Channel, SAS, SATA, etc. A little bit about KIOXIA. So KIOXIA was originally named Toshiba Memory Corporation. We're our own independent company now as of October 1st. So just in case KIOXIA doesn't ring a bell, we were Toshiba. But the way you pronounce it is KIOXIA. Everyone gets it wrong. Don't worry. All right, we've got a pretty wide portfolio of products as well, from client SSDs all the way through data center, hyperscale NVMe SSDs, SAS, SATA, etc. In spirit of what Cirrascale and others are talking about today, I'm going to be focusing in on compute nodes, etc. So compute nodes are, I like to call this section the need for feed. What are we feeding? We're feeding data. Data is food. Data is food for compute nodes. When you take a look at the market today, NVIDIA recently announced their A100 DGX. These are systems that are chugging data like crazy, and it's a huge improvement over the previous generations. So you want to keep these GPUs as busy as possible. You want to keep them fed. If they're not feeding, if they're hungry, then they're starving. And starving occurs when the GPU is waiting for DRAM and storage to offload, reload, and checkpoint training sets, which is where PCI Express Gen 4 comes in. Wanted to give a big shout out to guys like AIC, especially AMD, for enabling this PCI Gen 4 environment. So AMD's been out there for more than a year now, I think a year and a half maybe, with PCI Gen 4. And they're enabling the market with their EPYC Rome and Milan CPU and chipsets. And so we're just so pleased that they're able to enable this piece of the ecosystem. And why that ties into everything, as you'll see in the slides to come. But essentially, you want to feed the need for data with fast local and remote storage with PCIe Gen4 systems, SSDs, NICs, and NVMe over Fabric. So taking a look graphically at why local storage matters. Local storage is essentially inside of your compute node. You have to have storage inside of it, and that's what makes it local. During the training phase of machine learning, that happens to be the most resource-intensive set of operations. When you look at the data sets that are being sent back and forth, they're growing at an exponential pace. If you go get an MRI scan today, you can get up to 8K resolution on those MRIs, and those files are getting up to terabytes. And training sets can be thousands of images, so we're talking about training sets on the petabyte scale. And so whether you're running on the DRAM or on local storage, you want to make sure that the local storage is able to keep up with the GPUs. It's able to handle reads and writes as quickly as possible. It's able to do this with low latency because you want to make sure that the GPUs are always busy. They're always being fed. We've got some speeds and feeds here on sequentials, up to 7,000 on reads, up to 4,200 megabytes per second on writes, over 1 million random read IOPS, 70K plus random writes, and density. We're able to get up to 30 terabytes in a single SSD due to denser die NAND. So why would you want to tie slow storage performance in a system that's literally meant to chug data as quickly as possible? So we encourage you to go forth with Gen 4 SSDs. This is a CM6, our enterprise class NVMe SSD. A couple big highlights. It's our own stuff, our own controller, firmware, flash. Single port, dual port, same SKU. Dual port is used for high availability applications, redundancy, so you can have multiple paths to the same storage. Features our 6th generation of die failure recovery. So if something happens and one of your NAND dies fails, a die on a NAND package fails, the drive is able to recover, send a smart message to the host letting it know that a serious error has occurred. The drive is still fully operational, albeit with reduced performance. In terms of security, if you're dealing with customers or you're dealing with data that you need it to be secure and encrypted, we support a really large amount of security options. We're SIE, which is Secure Instant Erase or Crypto Erase. We also support TCG Opal, TCG Ruby, and we should be completed with FIPS 140-2 sometime in second quarter 21. Here are the performance numbers for the drive. Big key item for me is the random reads. It's over 1 million IOPS on a single SSD. It's just crazy how things have come along in the age of SSDs. On the storage lake, data lake side, so one of the things that a data lake wants to do is keep these compute nodes busy with data, right? Keep feeding the data to the compute nodes, let the compute nodes do what they need to do internally with it. And one of the ways that you're able to accomplish this is with PCIe Gen4, right? PCIe Gen4 enables much faster interconnects and local networks that were originally based on PCIe Gen3. You get things like NVMe over Fabric that have really come into play. And these faster interconnects means that more data can go back and forth between the compute nodes and storage nodes, which keeps everything active and it keeps the compute nodes fed. So why does remote storage matter? Well, we continually see improvements on everything that's within a storage network. Now the networking speeds have improved by quite a bit. They're now catching up to where SSDs are. And we're seeing cool technologies like 200 gig Ethernet NICs, dual and single port. We're hearing stories of 400 gig NICs to come out in the future. Rocky V2 and NVMe over Fabric deployments have become a reality. People are seeing that these are fast. They do what they say they're supposed to do. They reduce latency. And then again, the data sets that are out there, I'm talking about on petabyte scale, or at least on terabyte scale, lots and lots of files that have to be sent and received from the compute node to minimize downtime. NVMe over Fabric has become really popular because it has low latency. We've seen it. We know it's out there. We've seen studies that show that NVMe over Fabric environments, if you have local storage and remote storage, in some cases, the local and remote storage are very similar in performance and latency, which is crazy when you think about this is data that's going across a network. Okay. This is a CD6. This is our single port drive that's meant for data centers and for entry-level NVMe enterprise deployments. Great performance, similar in terms of the security features and everything else. Single port design, slightly reduced performance compared to CM6, and it's been a real great product for us in the market. Again, compatible, or it works with PCIe Gen4, also works with PCIe Gen3, and it's compliant to NVMe specification 1.4. Fantastic drive. It's been out in the market for almost a year now. We announced it last February along with CM6. So sorry to go really fast, but I don't want to get between you and happy hour. And I wanted to say thank you to you for attending, for spending time with us today. And I wanted to say thank you to all of my partners, including AIC, for putting this together. And I'd like to say cheers, if that shows up correctly. Cheers, and have a great day.
AMD's Madhu and Durthari will now tell us about AMD's EPYC 7000 series processors.
One of the really great things about the AMD 7002 series processors is the architecture advances that we've made. And one of those is with PCIe Gen4. And this allows you to double your PCIe bandwidth for your most demanding applications across HPC and enterprise. And one of those things with PCIe Gen4 is our valued partners that have developed PCIe Gen4 solutions. So first of all, with Mellanox, you are now able to get, with their ConnectX 6 solution, 200 gigabits per second of InfiniBand, which allows for extreme scale HPC connectivity. With Xilinx and FPGAs, you now have the ability to eliminate the bottlenecks that you've traditionally seen with acceleration solutions. With Samsung and PCIe Gen4 solutions, you now have lightning fast data transfer, eliminating the bottlenecks that we've typically seen in the past with PCIe Gen3 data solutions. And with Broadcom's new 200 gig Thor solution, you've eliminated the network bottlenecks that have traditionally been there in large enterprise environments. With PCIe Gen4, which delivers 2 times the I/O bandwidth, you can now remove I/O bottlenecks from your environment and achieve incredible scaling.
Hello, good afternoon. I hope you can see my screen. This is Madhu Indurthi from AMD. Okay, I'm gonna go ahead and get started. I hope you can see my slide deck here. I'm the business unit lead for storage and embedded here in Austin, Texas. I'd like to take a minute to thank our partners, AIC, KIOXIA, and Cirrascale for this excellent webinar today. We are elated here at AMD to see our PCIe Gen4 end-to-end solution being taken advantage of for some of the leading business cases here. A special shout out to our AIC partners who have arranged this webinar, so thank you, and thank you for your time today. So with that, I'm gonna jump in to our roadmap. We are excited to be executing on our leading data center storage solution roadmap. We entered this back into the foyer again around 2017 with our Zen 1 product line, which you may know them as EPYC 7001, also called Naples. That is the first generation AMD EPYC. Currently, we are shipping the AMD Zen 2 based second generation EPYC, also known as Rome. We are already executing, and we have initial production in Q1 with our Zen 3 based Milan product line, which is again the 7 nanometer industry leading solution. This will be our EPYC third generation solution. We are already executing very well on our fourth generation, which is our Genova Zen 4 based solution, which is targeted for 2023-24, and that would be our 5 nanometer DDR5 PCIe Gen 5 solution. So we have seen tremendous traction. We continue to see tremendous traction with our Rome and Milan product lines. We are pretty much in all the major data centers with over 50 AMD EPYC cloud instances. at Google, Azure, AWS, Baidu, Tencent, and a whole slew of other data centers. If we are looking at the partners, we are working with all our major partners in the industry, including, the device vendors like Samsung, KIOXIA, Pcie Gen4 like Mellanox. Also with our enterprise class storage customers like Dell EMC, HP, and not the least AIC, who we are partnering with on the 1U36 as well as the 2U4 node and a couple of other platforms for both storage as well as compute intensive storage solutions. On the scalable product line, I think this is, closer to our slide number 3, where we've looked at, at the entry level 2-core to 8-core, we have the R series, B series, and EPYC 3000 series that are ideal for the consumer NAS and cold storage. We go up to 16 cores with the EPYC 3000 that are ideal for JBOD solution as well as cold storage solutions. Now, the PCIe Gen4 based solution, which is what we are looking at today with AIC, KIOXIA, and Cirrascale, is the ROM-based 7002 solution. This is in a very nice, sleek 1U36 form factor, and they're taking advantage of our native PCIe Gen4. We've also seen a lot of traction for these solutions in all-flash arrays and high available storage solutions. Similarly, with our next generation, I think we are well placed in leadership position to go into all-flash arrays, high available solutions, backup restore, and cloud storage. If you are looking at a couple of feature sets that bring terrific value proposition to the market and for solutions and customers, you will see on enterprise storage, we bring in the native Gen 4. To date, we are still formidable when it comes to your value proposition of PCIe Gen 4 connectivity with 128 lanes of PCIe Gen 4. We are also enabling from the embedded team enterprise storage features like NVDIMM-N, hot plug, and PCIe Gen 4 based non-transparent bridging NTB. We also have various platforms and traditional storage platforms like SAS-based SBB, storage bridge bay, as well as all-flash arrays. Those are the dual controller solutions as well. So if you're looking at the value proposition for, say, a white box or ODM direct storage, we deliver up to 2.5x the storage capacity because of our connectivity, almost 3x the IOPS that you can get with the competition, 2.8x read-write bandwidth, and almost half the TCO when compared to the nearest competition. So we have a lot of flexibility. We also deliver ISAL and SPDK support for things like erasure coding, dedupe, and encryption. And lastly, on our last slide, these are an overview, high-level overview of our storage-specific enablement. We looked at non-transparent bridging, NVDIMM support, storage hot plug. We also have an 85-watt based ROM, which we call EPYC 7292P, that comes with 64 lanes of PCIe Gen 4, but with a very low TDP of 85 watts. We also support longevity from 5 to 7 years, depending on the SKU, and you can expect tier 1 support for storage appliance designed for any of the designs that you're working on. With that, I'll conclude my presentation, and I would like to thank our partners here, AIC, KIOXIA, Cirrascale, and special shout out to AIC for this webinar. And thank you for your time today. Back to you, Stephen.
Thank you, Madhu. So anyone have a question for AMD, Cirrascale, and KIOXIA? You can type your question in the question box, and we can have our partner to answer those questions. Okay, we have got a first question. This is for Cirrascale. Does workload directly affect the type of hardware I should use? So I will let David to answer the question.
Yes, workload definitely affects the hardware that we're looking to pick. In this particular usage model, this is a very large AI training system. So we really had to focus on very low latency and high throughput scenarios. If a workload was different, we may look something that's more scale out. This was designed for hardcore scaling up of the network and the I/O.
Thank you, David. We got another question for Madhu. So what's the max core count of an AMD processor today?
That's a great question. So for both our current Rome product line as well as our future Milan product line, we support anywhere from 8 core all the way to 64 core with the same footprint with pin compatibility. So the maximum is 64 cores.
Thank you, Madhu.
Yeah.
And another question is for Matt. What kind of a security feature does the KIOXIA drives have?
So for security, we support instant secure erase as well as sanitize. We have SED options for TCG Opal, TCG Ruby, and then if you have any really sensitive data that requires FIPS, we'll be completing our FIPS 140-2 certification sometime in Q2. Thank you for asking.
Thank you, Matt. Another question for you is, does it work in a U.2 backplane?
Yeah, there's a lot of fear and confusion out in the market considering around U.2 and U.3. For the SSDs that support U.3, they are also supposed to support U.2 without any restrictions. So if you plug me into a U.3 backplane, I'll connect up at 1x4 or a 2x2. You connect me into a U.2 backplane, I'll connect at 1x4 and 2x2. I have some circuitry internal to the SSD that maps it correctly to whatever kind of backplane I'm plugged into.
Thank you, Matt. Another question for Madhu. Which AMD processor have a PCIe Gen4 and how many lanes?
Good question. Both our Rome as well as Milan, the current and future generation, have PCIe Gen4 128 lanes from your bottom SKU to all the way to the top SKU with some exceptions.
Thank you, Madhu. Another question for Dave from Cirrascale. Normally, HPC need to be on-premise versus in the cloud. Why is this different now?
So we designed our cloud identical to how you'd build it on-prem. We have a long history of designing and building and ultimately selling systems in our past. And when we moved to be a cloud service provider, we effectively build the same type of architecture in our cloud that we would put on-prem for an end user. We're not virtualizing, which HPC hates virtualization. So we're a little different than the hyperscalers. They tend to look for elastic computing. In our case, we were really looking for production workloads. So we're designing and building it just as if it was designed and built and supplied on-prem.
Thank you, Derek. Next question is for AIC's Alan Yu. How did AIC make all the AMD PCIe Gen4 lanes available?
Yes, so for AIC, we took all the PCIe lanes and then divided between the network side, and then the rest we put it into high density connectors. So this way, all the PCIe lane will be available. So if you want to use it for storage, or if you have different needs such as add-on cards, or if you have a lot of GPU, we could pull it to GPUs. So we use we try to maximize the usage by using high density connectors instead of traditional lanes.
We call it Max.io.
Yeah.
It's been AIC's server slogan for over decades. Max.io.
Thank you, Alan. So I got another question is from John. And what is the life expectancy? How long can I get the same product on the current Epic product? It's more important for me to have no variations than the newest and the latest for this project. Madhu, can you answer this question?
Yeah, so that's a good question. Now, since we have pin compatibility with the ROM, which is our Epic 7002, as well as our next generation, which is Milan or Epic 7003 products, you have a lot of leeway here. ROM, depending on which SKU you select, we support 5 to 7 years of longevity. And Milan will be similar, starting from 2021. Does that answer the question?
Yes, thank you, Madhu.
Okay.
There's another question from Mike. How does a PCIe Gen4 link level reliability compare with SATA?
Yes, so for our server, we have internally we have linked to NVMe drive and also linked to SATA. And if you look at the AMD architecture, the PCIe lanes can be configured for PCIe or SATA. So that's the way for AIC to take advantage of having tri-mode. That's for the server side. If you're speaking about the CPU side, I'll let Madhu answer the second half.
I think this question is more to KIOXIA, because the question is asking about the SATA drives, the reliability between NVMe drive and also SATA drive. I guess I'm not sure my interpretation is right or wrong, but probably for KIOXIA. Question.
Matt, can you comment on this?
Yeah. Overall, speaking to like the longevity of products, am I following the string right? So for us, we've seen some pretty crazy trends in the data center and server and storage markets, right? As evidenced as on AIC's website, Cirrascale can tell you as well. Everyone's starting to scale up to NVMe offerings, and we're at a pretty crazy transition point for PCI Express. PCI Express Gen 3 was around for, I want to say, probably out in the market for 10 plus years. So everyone got very comfortable with it. Everyone knew how to work with it. And then, PCIe Gen 4 started shipping on AMD processors about a year ago, maybe a year and a couple months ago. And so from an SSD vendor perspective, it's been challenging because, on the server side, servicing several markets as a SSD vendor, the hyperscale market, especially the top 3 hyperscalers, those would be Microsoft, Amazon, Facebook. They represent probably 60 to 70% of the overall market for what was SATA drives, and now they've transitioned over to NVMe. So that's had some vendors. If you looked at the recent press releases from Intel, for example, Intel's new SSDs using their 144-layer NAND, they're only focused on PCIe. For us as a company, we, on the client side, continue to have PCIe. We've been leading the charge on PCIe for clients. On the hyperscale side and value server side for SATA, we actually sort of see SATA going into sunset. If you were to go to the KIOXIA website and type in life after SATA, you'd see that we're seeing the market shift over to NVMe and even SAS very quickly. As you watch what companies like AIC are doing, they also see that NVMe, there's just so many performance and endurance and latency gains over legacy SATA that it's hard to turn away from. And one of the biggest entry points, prohibitive entry points into deploying NVMe has been cost, right? Because there used to be a really large cost delta between SATA drives and NVMe drives, especially at the data center server level. And what we're seeing from an SSD point of view is the cost difference between SATA and NVMe, really SATA and NVMe, is coming down by quite a bit. So that's like, I have a product on my list called CD6. There are other products in the market that are similarly marketed as a in-between for a mainstream NVMe drive that you'd find in a HPC box, and a entry-level NVMe. I want 6x the performance of SATA. I want 1/4 of the latency. So there's a product line that is making the jump into NVMe a lot easier. Compounded by this is the jump from Gen 3 to Gen 4 that was very sudden. And then you may see press releases out there about Gen 5 coming a year or 2 years away. So very hard to invest in technology that you can be sure, at least from the SSD side, is going to be shipping for a long time. But the solace that you can keep to yourself is that all of the SSDs that are compliant to PCI Express always have to be able to work at the previous PCI Express. So the CM6, CD6, they link up Gen 4, they link up Gen 3, Gen 2, and Gen 1 PCI Express. So no matter what, you're always going to have an NVMe drive that works in your environment if you've made the transition to NVMe. I've already spoken for a long time, and I hopefully answered your question.
Yeah, so actually he has a follow-up. So he wants to know what's the error rate and at the link level, PCIe versus SATA, the reliability on that. If you give a quick comment on that, that would be great.
At the link level, that's, I'd have to table that one. So NVMe and PCI Express, I mean, for us, just looking at like AFR and things like that, we're at 2.5 million hours and a failure rate of, I want to say it's like 0.28. And in the NVMe and PCIe specification, there are a lot of registers that would correspond to link level errors that you can read from the smart logs. With Serial ATA, it's a lot less, how do I say, it's a lot less complicated when you're looking at errors from a link point of view. There's just a couple primitives in SATA that would indicate if you have an error, and then the host stack has to go off and take a look. Was it a link error? Was it a CRC error? There's a lot of things that go along with that. But for NVMe, I'd say Gen 4, honestly speaking, there's still some kinks being worked out, right? Intel is just now getting into the Gen 4 game with their platform. And so now they're starting to test all the SSD vendors with their stuff. And so, of course, there's going to be some minor differences on how the links are handled, what the signaling integrity is, and there's some growing pains with it. But at the end of the day, you're always going to link, especially if a drive has gone through PCI compliance workshops. PCI compliance workshops are held by PCI SIG quarterly, and everybody who wants to be determined as a PCI SIG compliant or PCI Express compliant device has to go through these tests, has to test with all the different hosts that are available. And if you're buying a drive that's gone through that certification process, you shouldn't worry about if the drive is going to connect or not.
All right, thank you, Matt. That answer is right on. And the last two questions for, I think both are for Madhu. one question from Andy is there any possibility of going smaller than the 5 nanometer in the future? Oh, sorry, it's a 5 millimeter. Is that sorry? Is that for the drive or?
That is for
I think
silicon processing.
that will be for the mat. I think it's a drive for the smaller than 5 millimeter thickness.
Well, the 5 is cutting it close, right? So M.2 today, you can get at 5 millimeter. You know, it depends on the size of the heatsink. There's another form factor called E1.S, where there's a bare board, and there is I want to say it's 5 millimeter. There's a bare
5.9.
5.9, 9.5, 14, and 25. So there are some options out there that are thinner, but the problem with going thinner and thinner is you leave no heatsink on top of your SSD. And as you go up to like PCIe Gen4, the power and heat that are generated by these drives is pretty intense. So as an example, my CM6 drive, we had to cap the sequential write performance at 4,200 megabytes per second because we very quickly hit the 25 watt maximum that you can do on a U.2 interface, right? It's limited to 25 watts. So we could have gone much higher in performance on sequential writes, but we had to limit it because of the heat. The drives get very hot very fast because, you know, when you're thinking about millions of IOPS or, you know, close to 6,000, 7,000 megabytes per second, that generates a lot of heat and that uses a lot of power. So if you're looking for something that is like a boot solution, or you're not looking for very much performance, then I would say it's appropriate to look for a device that has little to no heatsink. Heat sinks are super important, especially to the operation of drives, because you want to make sure that, you know, if you buy a fast drive, that drive, if it's always hot, is always going to be in thermal throttling mode, and you're never going to get the performance out of it that's advertised.
Thank you, Matt. Actually, Andy was correct. It's a full 5 nanometer. So I think this will be the last question. So Madhu, is that the CPU can go smaller than the 5 nanometer?
That's a good question. At this point in time, we are looking at 5 nanometer for our Gen4 timeframe. Beyond that, I think we'll have to defer that to a later time.
All right. Thank you very much, Madhu. All right, that's all for the Q&A. Thank you very much, everybody, and thank you, Madhu, Matt, and David for your answers, and also Alan. Now we'll do the closing, and we will show out the links for our happy hour. If you have any further questions, welcome to join our happy hours in the Zoom room, and our partner, David, Matt, and Madhu will be in the room to answer any further questions.
That ends the video portion of our webinar, but please rate this event. We value your feedback. We will post the presentation to www.aicipc.com. Please follow us on YouTube, LinkedIn, and Facebook. For future webinars, on January 20th, we'll have Computational Storage, Your Strategic IT Advantage. On February 3rd, Transform Static Architecture into a Dynamic Data Center in just a few clicks. On February 24th, it's Maximize Performance and Minimize Rack Space and TCO.